These 12 spinning circles are drawing a face. Every loop, corner, and slightly crooked eyebrow comes from one point attached to the final circle in this chain. Give the chain more circles, and the drawing sharpens until it can trace handwriting, coastlines, a bicycle, almost any closed path you hand it. That sounds like a trick where the answer is hidden somewhere inside the mechanism. It isn't. Each circle only knows two things: how wide it is and how fast it should turn. That's the entire instruction set. Radius, speed. Somehow, those tiny instructions cooperate into a picture. Watch the endpoint. The largest circle carries a smaller circle, which carries another and another. Their rotating arms add together, tip to tail. The last tip leaves this pale line behind it. For a moment, the machinery looks wildly overcomplicated. Then the line curls around the eye, crosses the cheek, catches the shape of the mouth, and suddenly the circles have drawn someone. Okay, that turn gets me every time. A pile of perfectly smooth rotations produces a corner sharp enough to read as an expression. Here's the mystery we're going to hold on to. Where did the face enter the system? None of these circles is shaped like an eye. There is no little face template traveling around the chain. If I hide the traced line, all you see is a collection of arms turning at steady rates. So the picture must be stored in the radii and starting angles, scattered across the whole machine. To see how that storage works, we have to break the chain almost completely. One circle first. What can one rotating arm actually draw? One arm gives us exactly what you'd expect: a circle. Its horizontal position slides like a cosine wave, while its vertical position moves like a sine wave, the same motion seen from two directions. Rotation is a pair of waves packed together. Attach a second rotating arm to the first tip, make it half as long, and let it spin twice per turn of the large arm. The endpoint no longer follows a circle. It bulges, pinches, and closes into a new curve. Change the small arm's starting angle and the bulge swings around. Reverse its spin and the curve folds the other way. Four controls appear: length, starting direction, speed, and whether that speed is clockwise or counterclockwise. The first arm lays down the broad motion. The second adds a repeating correction. At every instant, we add their arrows tip to tail, combining their contributions into one position. Add a third arm spinning 3 times as fast, and it places 3 smaller corrections around the trip. Higher speeds make finer features because they repeat more often before the drawing closes. That's the first real clue. Big, slow circles control the silhouette. Small, fast circles handle twitchy details. It's like building sound from a low note and higher harmonics, except the result lives in a plane and the endpoint draws a shape. Let's test that with a square, because a square is rude to circles. Its side stop and its direction changes instantly at every corner. Smooth rotations have no business making that happen. Yet with 5 carefully chosen circles, the endpoint already acts suspiciously square. So how do we choose those circles instead of guessing until the machine behaves? Choosing the circles starts with a move that feels almost too simple. Turn the drawing into motion. Put a dot on the square and send it once around the boundary at a steady rate. Now ask where it is at each moment. At time 0, it has a horizontal and vertical coordinate. Record those coordinates throughout the trip and the shape becomes a time signal: 2 synchronized squiggles, x of t and y of t. Any closed drawing can be treated this way, provided we choose an order for visiting its points and return to the start. This gives the circles their assignment. A rotating vector is a pure repeating motion. We compare each rotation with the moving dot and ask, how much of this frequency appears in the journey? Try 1 turn per trip, then 2, then 3. Try the opposite direction too, because plane motion can curl either way. For each rotation, imagine watching the drawing from a coordinate system spinning at that speed. If the drawing contains that rotation, part of its motion stops swirling and develops a consistent lean. Average the transformed positions and that lean becomes a vector. Its length gives the circle's radius. Its direction gives the starting angle. If the frequency contributes nothing, the transformed path balances around the origin, so its average lands near 0. If it matters, the average shifts away. There it is. The drawing chooses its own circles. This is the Fourier transform in working close. It measures how strongly each rotational frequency appears in a path. But one detail remains. We usually receive a drawing as a finite list of sampled points. Can a limited collection of dots really reveal all those circles? A finite collection of dots is enough to build a finite collection of circles exactly. Keep 64 equally spaced moments from one trip around the drawing. The discrete Fourier transform turns those positions into 64 rotating components. Add them together at the sample times and the endpoint hits every original dot exactly. Exactly matters. Between the dots, the reconstructed path may curve differently, but at each recorded moment it returns to the data, aside from numerical rounding. For frequency k, take every sampled position, undo k turns of rotation according to that sample's time, then average. The result is the coefficient c sub k, a vector whose magnitude becomes a radius, whose angle becomes the initial direction, and whose k determines its speed. Negative k means clockwise. reconstruction reverses the recipe. At time t, rotate every coefficient by its assigned frequency and add them. Analysis separates the drawing into rotations. Synthesis stacks them back into the drawing. Now rank them. Long coefficient vectors visibly steer the path. Many others are tiny. Keep only the largest handful and the endpoint misses the sample dots, yet the drawing may remain unmistakable. That is why 12 circles could make a face. They preserve the motions carrying most of the shape and discard small adjustments. Watch the data rebuilt with one component, then 3, 8, 16, and all 64. First comes location, then overall scale and direction, then lobes and bends. Fine corners wait for the fast small circles. Circle count acts like a detail knob. But that raises a sharper question. If every ingredient is smooth, what happens at a genuine corner where the path's direction jumps? The corner appears through a tiny rebellion near the turn. With a few components, the square rounds off. Add more and the bend tightens, but a ripple remains on either side. More circles squeeze it into a narrower region, though its peak fades surprisingly slowly. This is related to the Gibbs phenomenon. A finite collection of smooth waves cannot cleanly reproduce a sudden jump. Our square's position remains continuous, but its direction changes abruptly, so the effect is gentler than the classic example. Still, smooth ingredients are imitating something infinitely sharp. And I love what the machine does here. It spends its fastest circles exactly where the path demands sudden change. Along a straight edge, the corrections cooperate. Near a corner, they crowd together, overshoot, reverse, and settle onto the next side. With 5 circles, the square looks inflated. With 21, the edges flatten and the corners gain a slight wiggle. With 101, that wiggle compresses so close to each corner that the trace reads as a square unless we zoom in. This gives almost anything its honest meaning. For a reasonably well-behaved closed path, enough Fourier components can approximate it as closely as we like. Exact sharpness may require infinitely many. A finite drawing sampled at finite points can be matched at those points with finitely many components. Keeping those claims separate stops us from calling the circles literal magic. There is another catch. Our curves close neatly after one trip, but drawings often contain separate strokes, interior details, and jumps. A face has 2 eyes. Handwriting lifts the pen. How can one endpoint trace disconnected pieces without drawing ugly bridges between them? A single endpoint always traces one continuous route, so disconnected strokes need a choice. The straightforward option is to connect them, draw the first eye, travel to the second, then the mouth, and eventually return to the starting point. Those travel segments become part of the mathematical path. If we display every segment, faint bridges cross the face. Sometimes the endpoint races across them. Sometimes they slash through the nose, which is less charming. Instead, lift the pen during designated intervals. The circles keep moving through each connector, preserving one continuous periodic path, while the renderer hides it. At the next intended stroke, the pen returns. The math never teleports. The displayed drawing can. We can also change the route's timing. At constant speed, equal times cover equal distances. Give a detailed region extra time and samples concentrate there, directing more Fourier accuracy to that feature. Same picture, different timing, different coefficients. The circles encode the journey, including its schedule, not geometry alone. Point order matters even more. Shuffle the samples and the reconstruction still visits every point at its assigned time, but the connecting curve becomes a frantic knot. Order them sensibly, and a few large coefficients capture the path cleanly. Compression depends on structure. Now feed the system a handwritten word, sample the pen route, include hidden jumps, calculate the coefficients, then sort the visible chain by circle size for readability. 8 circles give a loose gesture. 32 make the word legible. 256 catch small hooks and uneven, pressure-like turns. The answer is nearly complete. One piece remains. Why can rotating circles describe such a huge family of motions in the first place? Rotating circles work because repeating motion has a natural set of coordinates, and these rotations are those coordinates. On graph paper, we describe a point with horizontal and vertical amounts. For a periodic path, we describe the whole motion using amounts of each frequency. The crucial property is independence. Over one complete cycle, different integer rotations balance against each other. Compare a 1-turn rotation with a 2-turn rotation across the full interval, and their alignments cancel. The same holds for every unequal pair. Mathematicians call this orthogonality. Visually, our averaging trick can isolate one frequency without the others leaning into the result. That is the engine under the Fourier transform. Each coefficient answers one question: how much of this rotation is present? Once we know every answer, adding the rotations rebuilds the original sampled journey. Now the opening face looks different. The largest circle carries the broad sweep around the head. Another pulls the trace into the eye loops. Smaller, faster ones sharpen the mouth and tuck the line around the nose. No circle contains a recognizable feature by itself. The feature exists in their coordination across time. Let's run the full chain once more. 12 circles draw the rough face. 50 make it identifiable. 200 trace the asymmetries that make this drawing feel handmade. Speed doesn't simply indicate how quickly the pen travels, it labels a global frequency, a pattern repeated across the entire trip. That distinction keeps pulling me back. Every tiny fast circle adjusts the whole drawing at once, yet those global adjustments assemble into a wrinkle here, a corner there, one brief hook in the line. A picture becomes motion, motion becomes frequencies, and frequencies become a picture again. The circles never learned what a face was, they only learned how to turn together. Apparently that was enough.